in the last class we showed that if sigma I and pi I is equal for some I 1 or more, then the whole polynomial hierarchy will collapse to this class sigma I. Okay. And it also meant that if sigma I plus 1 did not grow bigger, if it was equal to sigma I, then also the same thing happens. Okay, so that's why polynomial hierarchy is interesting, because things that happen at the lower level, if classes collapse at the lower level, then the whole hierarchy collapses to that level. And in particular, you get this simple corollary that if P and NP are the same, then everything in the hierarchy is easy. Okay. P equal to NP means that the polynomial hierarchy is also solvable in polynomial time, and obviously the converse is true. Okay, this is if and only if. So it makes P not equal to NP question even more interesting, because you actually are showing that the hierarchy is not in polynomial time. Now you can ask for the hardest problem in PH, right? Complete problems. So is there a PH complete problem? Like NP completeness, is there also PH completeness? Now suppose there is. Okay, suppose A is PH complete. Under polytime reductions. So then what happens is, so A in AH, A in PH, right? PH is a union of sigma i's. This means that A is in some sigma I. Right? If A is in the union of sets, then it is in some set. So this is sigma I, say, which means that since A is PH complete, this would mean that PH is in sigma I, which means that actually PH has collapsed. Okay, so if there is a complete problem, PH complete problem, then actually PH collapses. So in other words, if PH conjecture is true, then there is no PH complete problem. So PH conjecture implies that PH complete problems don't exist. Okay, that's an interesting thing, that actually complete problems don't exist is what we believe. So this has a very interesting consequence, simple consequence. Since PH complete problems don't exist and PH is in P space, so it also means that PH is strictly smaller than P space, assuming the conjecture. PH conjecture implies that PH is a proper subset of P space. You see this trivially now, because PH conjecture, or let me say, so suppose PH is equal to P space, then it will mean that QBF is PH complete. which would mean that pH conjecture can't be true. Right. So this means that pH will be smaller than P space, assuming the pH conjecture. So there is no pH complete problem, but you can still ask whether there are sigma I complete and pi I complete problems. And intuitively they should exist because NP complete problems exist, which is sigma 1 complete. So maybe SAT can be extended to sigma 2 complete problem. So what will that be? So we'll call it sigma I SAT. So it will again be about Boolean formulas. Boolean formula phi. U1 to Ui are not bits, they are actually, think of them as strings, Boolean strings, I Boolean strings, and such that phi x bar is a Boolean CNF with a partition of x1 to xn into u1 to ui such that there exists u1 for all u2 there exists u3 dot dot, finally this qi quantifier on ui, phi should be true. Okay, so this is sigma is SAT. It's the collection of those, its yes instances are these Boolean CNFs like SAT, except now there are quantifiers on all the variables. Okay, so a collection of variables which we are calling U1, there exists quantification. Then another collection of variables U2, obviously disjoint from U1 with for all quantification dot dot. So I distinct quantifiers are there on the n variables, and under this quantification phi should be true. So remember this natural generalization of SAT and observe that sigma I SAT is not quite QBF, right? Because in QBF, every variable, there were n quantifiers actually, so every variable was quantified alternatingly. That's not the case here. Here actually a collection of variables U1, all of them have the same quantification, and there are only constant many distinct quantifiers, right? So this seems to be very much lower than QBF in hardness. And second point is sigma 1 SAT is just the usual SAT, right? So in sigma 1 basically all the variables are quantified with their exist. So that's exactly the uh, instance of SAT, Boolean formula where there is a satisfying assignment. And our theorem is that sigma I SAT is sigma I complete. Okay, just like sigma 1 SAT is sigma 1 complete, so SAT is NP complete. Let's now do this for sigma 2. So by definition, sigma I SAT is in sigma I. Right? That isn't a problem because there were only I quantifiers. So it's in sigma I. We just have to show that it's hard. So let's take a language in sigma I. So any language in sigma I has a corresponding polytime Turing machine. M. That's the verifier, right? That is what happens after all this, all the I quantifiers. The verifier sits, which is polytime Turing machine. So convert that into Boolean CNF by Cook-Levin reduction. Okay, and so what you will get is an instance of sigma I SAT. The proof is almost direct from Cook-Levin. So computation of M given U1 to UI is captured by CNF formula where CNF formula phi by the Cook-Levin reduction. So this reduces the question whether X is in L, whether X is a yes string of L. This gets reduced to sigma I SAT expression. To the truth of the expression there exists U1 for all U2 dot dot QI UI phi X U1 dot U1 dot dot UI, right? So phi is basically simulating the computation of Turing machine M given the kind of these certifying strings U1 to UI, and whether the answer is 1 or not. That is what the verifier checks. We have expressed it as a as a formula, so we can remove equal to 1, and then the quantification on top of it, right? So this has reduced L to sigma I SAT. L has been reduced to sigma I sat in deterministic polynomial time. So which means that sigma I sat is sigma I hard. And since sigma I sat is trivially in sigma I, so we have a sigma I complete problem. Okay, so this was basically Cook-Levin. And in a similar way, we can also work with pi I sat. So pi I sat will start with for all quantification. So phi u1 to ui such that phi is a Boolean. Now D and F, right, the complement of C and F. Phi is a Boolean D and F with partition of the variables into u1 un not n I, such that for all u1 there exists u2 dot dot qi ui phi of u1 to ui is 1, right. So it's the same as sigma I sat, except you start with for all in the expression instead of there exist. Okay, yeah, this equal to 1 is implicit here. Still, let us write it. And just like the proof above by Cook-Levin, you know that pi I sat is pi I complete. So we have now complete problems for it is different from every sigma I, and so there is no single complete problem for pH, right? Because if it existed, then pH will collapse. So that will contradict pH conjecture. So to understand pH further, and in fact in a better way than what we did right now, we will define pH now through oracles. Okay, and that will be a more interesting description. So pH via oracle Turing machines. So think of what we did with NP, right? NP we defined via quantification, and then we defined it via NDTM. So recall that sigma 1, which is NP, this actually represents NDTM computation. So what does the polynomial hierarchy represent? In particular, what does sigma 2 represent? Is it representing some special Turing machine computation? That's the goal. So let's first define how we'll use the oracles. So to answer this question, so for complexity classes C1, C2, define the class C1 with oracle C2. To mean what the notation suggests, that assume that problems in C2 are solved immediately, and assuming that, what can you solve by algorithms for C1. Okay, so algorithms for C1 have this extra power now to actually call subroutines from problems in C2. So it's the union of C1 to L for all problems in C2. Okay, so this is L goes in C1 using oracle L. Okay, so this basically algorithm doesn't have to solve L. It will assume a solution for L, I mean some subroutine for L, that's the oracle, and then do what C1 does. Okay, C1 is also a collection of problems. So think of you can think of C1 as NP and C2 as NP, or even simpler, C1 as P, L C2 as NP. So let's see what happens. So P raised to NP, right? It's a polynomial time computation using NDTMs, polytime NDTMs. So that is what? That's actually the same as P raised to SAT. And then we don't know whether it is bigger or smaller than NP. So that we don't know. Right, that's an open question. So intuitively, P raised to NP should be bigger than NP. It certainly contains that. It certainly contains NP, because if you can solve SAT via oracle, then you can also solve any problem in NP, because SAT is NP hard. But we don't know whether it is strictly bigger. Right? So P raised to NP is now a new complexity class, potentially. And similarly, NP raised to NP is NP raised to SAT. If you have SAT as an oracle, you have whole of NP as an oracle, and vice versa. And so this definitely contains P raised to SAT, but we don't know whether it's proper. Right? So we are actually building classes above NP potentially. From NP we went to P raised to NP, from P raised to NP we went to NP raised to NP. And we can keep doing this. So what we intend to show is that NP to the NP is really sigma 2 that we had defined. Okay, this is what we will show. So that gives you a new insight into these quantifiers. Okay, so there exists for all is like an NDTM calling another NDTM oracle. So that's the theorem. For all I greater than equal to 1, sigma I is NP raised to sigma I minus 1, which is NP raised to sigma I minus 1 sat. That's the complete problem. Okay, so if you give an NDTM sigma I minus 1 oracles, then you actually get sigma I exactly. Right, so the proof is just working with I equal to 2. I equal to 1 is clear, NP is equal to NP. Maybe I write that down. So I equal to 1 is just saying that sigma 1, which is really NP, is NP to the sigma 0, which is P. Giving an NDTM oracle from P doesn't change anything. So that's clear. The first interesting thing happens, I equal to 2. Okay, so need to show that sigma 2 is NP to sigma 1 sat, which is sat. Okay, so how do we show that? So let's start with the case. Let's take a problem L in the left hand side, which is sigma 2, and we'll put it in NP to the sat. So then there is polytime Turing machine M and constant C such that for all input strings X is in L if and only if there exists U1 for all U2 MX U1 U2 outputs 1. Okay, that's the definition of sigma 2. Now how can we put this, how can we solve this expression in NP to the sat? So let's focus on, so I'm skipping the details of this U1 U2. You already know that it goes without saying now that U1 U2 are kind of certifying strings which are of length poly in the size of X, right? All that goes with the definition. We'll focus on this part. Okay, this part is like KANPUR-NP. So it's like sat bar. Right, so it is like an NDTM is using sat bar. Right, that is basically how we'll put the problem in NP to the sat. So the associated language L prime, which is y comma z string for all U2 M y z U2 1. Right, so this language L prime, which we are just picking from this sat bar part. So yz, think of yz as xu1, and then for all U2 this computation, verifier computation should be true. So this language is clearly, I mean by definition it's in KANPUR, it reduces to sat bar. So associated language L prime is in pi 1. Okay, that's a simple observation. And this means that L prime bar is decided by an oracle to SAT. Right, so L prime bar is in sigma 1, which is whose complete problem is SAT. So L prime bar you can reduce to SAT. Or you can solve by calling SAT instance. So this means that L prime bar is in P to the SAT, which means L prime also. Right. So the good thing about oracle is that you can do negation here. So you cannot do negation in an NDTM. We don't know how to do it in the same time. But in the oracle, using the oracle, you can do negation. Okay. And so now this equation that we had, this equation 1, we can now use this fact of using SAT oracle to rewrite it. So rewrite equation 1 as x is in L if and only if there exists a u1, x u1 is in L prime, right? X u1 we have now put in L prime the way we defined above, which is in P raised to SAT. So this means that L is in NP raised to SAT, right, which means that sigma 2 is in NP to the SAT. Okay, so we have proved the first part, that sigma 2 is actually contained in NP to the SAT. The way in the last step what happened is that these choices for u1 that an NDTM will make and keep making calls to L prime, right, which is really SAT bar. So in fact we can write it like this. Yeah, these are the oracle calls to SAT. Okay, and this is what we are using now. We are using here. First we are using that L is in NP to the L prime, which is contained in NP to SAT bar, which the negation you can do in the oracle. So you get NP to the SAT.